Okay, 23.2 grams of ethane. And I will always give you the formula in this class. In your next class, they're going to just say a chemical, and you're going to have to come up with a formula for it. Okay. Ethane is C2H8. Okay. Ethane are burned and 34.5 grams of oxygen are consumed. Two givens. How many grams of water are produced? And I mentioned here the actual yield also. So you're going to have to calculate percent yield and how much product is made, which is going to be water. Okay, so in your mind, when you did the bicycle thing, you went, okay, there are 2 wheels per bicycle, and we have 10 wheels. So 10 divided by 2 is 5 bicycles. That's what you did in your head. Okay, we're going to do the same thing with grams now. So let's start. We're going to have to do 2 calculations, one for each given. So let's start with the equation. Ethane is C2H8. And again, on the test, I will give you the formula for the chemical. And we're burning that in oxygen. And normally, when we have a gas, it's hydrogen gas. Yeah. Sorry? A week from tomorrow. The Saturday before break. So whenever we burn most things in the world, we produce carbon dioxide and water. Okay, is it balanced? No. So it's balanced now. How do you know it's balanced? Because the left equals the right. So inventory. All right, so now we have 2 givens. We have one is the 23.2 grams of ethane. And we need to figure out how much water is made. Okay, so the first thing we're going to do is, like all stoichiometry, there are 3 steps. Oh. Okay, so the first step is to get the given into moles. On the right. No, there's 12 on the right. 4 and 8. Oh, wait a minute. 4 and 4 is okay. Ferguson, you did it again. Okay, so we need to convert that 23 grams into moles of ethane. Okay, so the molar mass for ethane is, we have two carbons at 1201 apiece, 8 oxygens at 1.01 each. So that's 3210 grams per mole. You ever know where those numbers came from? Periodic table that you're going to be given on the test. Okay. Okay, so that's our grams will cancel. Now we need to go from moles of ethane to moles of water. That's a 1 to 2 rate or 1 to 4 ratio. Water is 1802. Okay, so if we're just looking at ethane by itself, you're going to end up with whatever this is. Let's see here. Okay, now we need to do the calculations on the other given. And that is 34.5. Okay, two oxygens at 16 apiece is 32. Okay, now we need to go from O2 to water. And let's see, O2 is 4. And water is 4 also. Okay, and then that's 18. 102 grams per 1 mole. Okay, so what limits the reaction? The ethane or the oxygen? Exactly. I want to go with the one that makes the least amount. Just like with the bicycles, we had lots of frames left over. We have 5 frames left over. So limiting reactant is going to be the oxygen gas. Now, the next part of this is how much is left over of the ethane. Another calculation. So we're going to use the oxygen to start with. I'm going to see how much ethane is used when we use all the oxygen up. And this ratio to ethane is 1, and to oxygen it is 4. And then molar mass for ethane is 32. Now, this is going to be how much ethane is used with the given amount of oxygen. And this will be excess ethane. Okay, so that's how much ethane we used up. Now we have to do one more calculation. That is how much is left over. That's how much we used. And we started with 34.5. We started with not 34, that's 23.2 ethane. We used 8.63. Okay. Okay. One more calculation is I want to know the yield. And when we do these calculations up above, we are calculating the theoretical yield. So theoretically, we could get 19.4 if everything went perfectly. Well, guess what? Life is not like that. Just ask anyone who's been in a relationship knows that. Okay, okay, we actually got 567. So it's actual minus theoretical over theoretical, all times 100. That'll be the percent yield. So we have 567 minus 19.4 times 100. And okay, so that is a typical limiting reactant problem. Now you're going to get one of those for the test, and it's going to be a take-home problem. Hang on, you get 1A, you'll have to do the in class during the test. 2A depends on the instructor, and 3A you'll have to do in class for the test. Okay. All right, so I'll post this. I'm going to do another example now. I'll post your take-home problem very soon. Plenty of time to do it. But this is real life chemistry, what we just did. One, you never get perfect yield. One item to start with, but it's a reaction output. Now, sometimes it will be kind of rigged, so there's one in excess, big time. If it's big time excess, you don't have to do the two calculations. Because you know the one that's in big time excess is not even the one that the reactant. If the reactants are kind of close together, then you definitely have to do all these calculations. Okay, so you have 4 calculations, 5 if you count yield. First 2 are to determine what limits the reactant. Yeah.
Water left over, but we're not using that number in for yield. Why do we need to find excess?
Yield.
I know, but I don't see it in the calculation.
Okay, so okay, so the theoretical yield is 19 grams of water. Okay. That's here. Okay. All right. And I said you actually got 567. So then you have to calculate the difference between those two over the theoretical. The problem will ask you how much is left over. Yeah. Yeah, that's a good point. Her point was, I didn't ask for the excess. Why did you calculate it? Right? Okay. Normally, they always ask for. So that's a really good point you made. Okay. So normally you're going to have to answer excess, which limits the reaction. And secondly, how much did you have left over of the other one? Okay. And let me go through one other thing here. Okay, so let's go back to the balanced equation. You start with two items, right? Ethane and oxygen gas. Which is totally consumed? The oxygen or the ethane?
The oxygen.
The limiting reactant is always consumed 100%. And since oxygen is the limiting reactant here, it's 100% consumed. And the other one is partially consumed. That's why we did the calculation of how much is left over. Okay, so the limiting reactant is used 100% of the time. And if you look this up on Google, frequently that's what they'll say. Which reactant is consumed 100%? They don't tell you how to calculate it. They just say one that's used 100%. So if on a test I ask you what is meant by limiting reactant, you need to say one of the two reactants is consumed 100%, leaving excess of the other one. Okay. Now, sometimes they're perfectly matched, like in an automobile engine. We have a computer in there that does these very minute calculations to determine how much oxygen you need and how much fuel is to be mixed together to burn effectively with the least amount of fog and the most power. You always balance and throw in economy as well. Normally, you don't have that perfect ratio. Normally, you have more of one than the other. But and a chemical engineer, that's what their job is to do. They're working for automobile manufacturers, and they will tune that engine based on the computer what those ratios are. Now, another interesting thing, we live, well, some of you don't, but I live at sea level, basically. I live in Natomas, close to the river. So I'm basically at sea level. You guys, a lot of you don't live in sea level. In fact, if you're willing to guess 100% of you don't live at sea level, you live somewhat higher. The higher you go, the less oxygen you have. So our good old computer has a sensor, an anemometer, to determine what that is, what percent of oxygen that is. And that goes into the calculation on doing the perfect stoichiometric ratio between gasoline and oxygen. Now, back in the old days, before we had these computers, we had carburetors. And the carburetors were not that smart at all. They had a constant ratio of fuel to air, regardless of what level you're driving at. So the higher you got, the richer that combustion was. And it got to the point where sometimes you can really feel the difference in power. And you certainly, if you ever pulled out a spark plug after you got back from a trip to the mountains, it was usually cruddier looking because it didn't burn completely. Computers fixed all that. All that. Sometimes people that lived in the mountains in the olden days, again, would actually change the jets on their carburetor to correspond to the level of oxygen up at a certain altitude. Like if you lived at Tahoe and you never left Tahoe. Some people just go up there and die. They never feel it. In that case, you could change the jets in your carburetor and be fine. Because you don't have to worry about driving down where it's low and messing up that ratio. Modern cars, again, just do all that. That's why it's a pain when that little chip goes out. Now, a lot of times you can take that little chip and replace it with another chip, and that'll change the performance of your car. And sometimes that's illegal, like 99% of the time. It changes the smog coming out the rear end. And that chip is optimized to give you the most clean air, most power, most economy. As soon as you change that chip out, none of that holds water. But if you want more power, that's a real easy way to go. It's just a plug and play. Okay. So does this calculation make sense? Now, I'm going to I'll probably use this next semester. There, I fixed it for you. Okay, again, any questions about this? Okay, so right off the bat, you have to do two calculations to determine how much product you have. The one with the least amount limits the reaction. Then you calculate how much of the other one you actually use. So you start with a limiting reactant. In this case, it's going to be oxygen. And then we're going to see how much ethane is used. And that's what this calculation is.
Then H2O, the carbon dioxide.
Yeah. Mhm.
And it would, same thing.
Correct. Yeah, very good observation. So it doesn't matter which product you choose. You choose it for both. Sometimes limiting reactant problems don't ask you that. They'll just say how much product is made. And then you get to choose one. And
So because the question is asking about the water, that's why you chose water.
Yeah, exactly.
It's asking about the carbon dioxide.
yep, exactly.
Okay, gotcha.
Yeah, good question. All right, so let's do one more. Okay, okay, 23 at STP, extremely important, of ethane are burned and 34.5 grams of oxygen are consumed. How many molecules of water are produced? How many? That means we're going to use Avogadro's number, 602 times 10 to the 23rd. All right, so we can do the same thing. Using the same equation, which I'm going to put over here. Bless you. Okay. So we have ethane burning. Okay, so we have two givens. And I want to know how many molecules of water are produced. And then we want to know how much excess we have of the non-limiting reactant. And I want to know the percent yield. Okay, so it's going to be 5 more calculations. All right, we're starting off with 23. Notice, as soon as I said liters of gas, I had to say STP. Now in this class, again, we're going to assume it's at STP. You can't assume that when you get to 1A, 2A, or 3A, however. But if it's at STP, we can use the 22.4 liters per mole. So let's start with the ethane. First step, always cancel the given, convert to moles. Applies to STP. It's real important to remember that. Okay, now we need to, and we're still talking about water. So the ratio is 1 to 4. And water is okay. I'll see how many molecules of water we've just made. Okay. That's for looking at the ethane. Let's look at the oxygen now. We're at 345. And the molar mass for oxygen is oxygen gas, 32. And we want the ratio from the balanced equation. It's going to be 4 and 4. And then water is now again, we're using the 602 times 10 to the 23rd because we want to know how many. Key that in, that question, how many? Avogadro's number. Put those two words together.
Where they're both four.
From the balanced equation.
Oh, yeah,
That's
but so, as you're going through the numbers, like first you divide by 32, but do we multiply or divide by 4 or just skip it? Actually, we got much.
well, let me give you two answers. If you're comfortable with math, skip it because 4 over 4 is 1, right?
Yeah.
If you're not comfortable with math, put the 4s in each time.
So multiply by 4 and then just divide by 4?
Yeah.
Yeah. But
Okay, so oxygen limits the reaction again. It produces less molecules. Yeah. Yeah. Oh, I mean, it's actually should be molecules over mole. I just. And this is an L also. Okay, so what's the limiting reactant? Produces less molecules of water, hence it's the limiting reagent. Now, when you see these problems, sometimes they'll say, what's the limiting reagent? Sometimes they'll say, what's the limiting reactant? We always work with reactants in this type of problem. Like when I was going through school, they always said reagent. In every book I've looked at in the last 15 years is reactant. Reactant, in my opinion, is more accurate than reagent. The reagent could apply to the reactants or the product. Okay, so now we know oxygen again is the limiting reactant. So let's see how much ethane is used if we use 34.5 grams of oxygen. So we're going to start with the limiting reactant. It's going to be oxygen. So oxygen needs to be on the bottom here. In this case, we're looking at the ethane. And this will tell us how much of the ethane we used up. Okay, so we've used 1.62 times 10 to the 23 molecules of the non-limiting reagent. Now we subtract that from what we started with, and it'll tell us how much is left over. Okay, so we started with there's a dilemma here. How do we subtract liters and molecules together? They're starting with 23.2 liters. And I just calculated how many molecules of ethane are used. So there's a conundrum here. What's the conundrum?
Calculated for liters instead of molecules.
Yeah, we have liters and molecules. You can't subtract them. We have to convert one to the other. So we can either convert everything to molecules or everything to liters. Doesn't matter, as long as the units are the same. That's what I'm getting at here. Okay, so let's convert the liters to molecules. Okay, so we're starting with 23.2 liters. And that's of the ethane. This gets us to moles. And if we multiply 602 times 10 to the 23rd, get us to molecules. Does everyone understand why I had to do that? Can't subtract something or add anything if the units aren't the same. Yeah. That's any gas at STP. It's 22.4. Doesn't matter if it's hydrogen gas, water vapor, uranium hexafluoride, still a gas, 22.4. But again, only at STP though. And then we have to use the ideal gas law, which we're going to cover a tiny bit when we have a lab on gases. That's the ideal gas law, and it'll convert whatever you want to whatever. Okay, now we have to subtract. I have to do the calculation. Okay, so this is what we started with. Okay, and how much do we use? Well, we used 1.62 times 10 to the 23rd, and we started with 6.24. So we're going to subtract those two, and that'll be the excess. Okay, those are two very representative limiting reactant problems. Worksheet, you practice on limiting reactants that you like with answers. And then the take-home problem that I'll post soon in the morning.
How come we missed our exercise here before? A little bit. Last time we missed our.
Well, this is the, ething. Starting.
I don't know. The last time we did actual minus theoretical over theoretical. And this time it's theoretical minus actual group theoretical. Like you see the two on top. David,
Yeah, we have an actual minus, yeah,
That's it, but
Yeah, theoretical minus, it doesn't matter if it's actual minus theoretical, is that what you mean?
yeah, because last time it was actual minus theoretical.
Yeah, it's, absolute value, so it doesn't matter. Because if you calculate what I did before, you end up with a negative percent. And those two goes positive with, percent yield. So is that your question?
no, I'm still thinking for it. The question, like, if it wasn't it, higher.
We're supposed to use the water. Basically,
Okay, so let's make sure I get everything right here. Okay,
I don't.
oh, I see what you mean, instead of using the ethane,
Yeah.
ah. Yes. That's what I should have done. Very valid point. Yeah, we should have used the, okay, actually, I did use the right one. Because it's the oxygen we converted to, so this is the, this is where you're, this number here should be what? This number should be 649. So this number here should be, Okay. I used the wrong numbers. Try to go. Molecule rather than grams, yeah.
So the problem is asking for, how many molecules of water is used?
On the yield.
Go to accidentally, because those numbers are the H2Os.
Yes. Working with water because that's the product. Huh? Okay, we're supposed to be working with product. Not. Product. No. We're using oxygen to burn it. Not produce. One.
Where
Is it? Yeah. Now, the gram problem is because I had a mismatch of units here. We had to convert back and forth. This second one was a lot of conversions, where the first one was grams to grams. Okay, well, first of all, the limiting reaction is going to be a take-home problem. And it's going to be more like the first one.
it's gonna be on Zoom.
Okay. I should have made this second problem similar to the first one. Okay. Okay, are there any more questions about these guys? All right, so to answer her question about what's going to be on the test. Okay, so we've got periodic table organization. Remember we did that? We talked about metals versus non-metal. Yeah.
So what chapter does the test cover, chapters all the way through 7 or?
It covers, most of it is on the one that says quantifying. The name of that chapter. It gets into mole, balance equations, and stoichiometry. You. They would have their book with them.
Older version, but
That's just. Okay, it's gonna be chapter 7 and 8. And chapter 7 is chemical reactions. We'll talk about balancing chemical reactions, and then chapter 8 is quantities and chemical reactions.
Yeah.
Okay, so periodic table organization, things like metal, non-metals, metalloids, things like columns. Remember, there are 4 groups you had to know. You had to know alkaline metals, alkaline earth metals, halogen, and noble gases. And I'm gonna put that, give you a periodic table, and we have to circle all of it. Lewis dot structures, I give you a formula. You write the Lewis dot structure for it, and you 2 of them. One of them is gonna be, you have to write 2 alternate structures. Get the given formula. Balancing equations, conversion, that's like grams to number of molecules, that kind of stuff. And then the stoichiometry is whatever last Saturday. And today. Right?
What about the extra credit, balancing equation, do we bring that to this test?
Yes, so bring that in. When you turn your test in, you staple it to the back. There's an extra credit balancing equation. I gave you. It's under. If you do a search on files extra credit, you'll come up with. These should all be the same.
We can just do that and then bring it.
Yeah. And then staple it back your test when turning. Now, for those who haven't tried this yet, I want to warn you, because it's extra credit, it's going to be hard. Also, don't be afraid of the coefficients being large, like over 100. It's nothing yet. Two ways to work this: guess and check, and a matrix method using reverse row echelon formula. If you've never heard of that before, that's because you haven't had linear output. I'll say there are 2 ways to do it. Okay. All right. Now the handout I gave you is the dry lab for today and tomorrow. Yeah. It's on Canvas. Yeah, but Canvas file, and the top of file is a search. Put in extra credit. I forgot what unit, I changed the units around for once. How are you guys doing?
So Rylab 12 is due tomorrow, right?
Yeah.
And that's just the first like couple of columns.
Not even the first couple of the second column.
Okay.
Just the Lewis dot.
Okay. And then this is for this.
That'll be due a week from tomorrow.
Okay.
Oh, on that worksheet I just gave you, do problem 2 last. And it's not any harder than the others. What's the reason I want you to do it last is the formulas are complicated. And I can balance the equation for you. I don't want to spend a bunch of time balancing. Okay, so do problem 2 last. I gave you the answers. So everyone should get a 10 out of 10 on this lab. Unless you don't want 10 out of 10 or more. Okay. And again, you can do this at home if you like, or you can You're allowed to move, raining out and then we're going to.
That's what is it?
So.
So. Okay,
So I had a question about the dry lab. I printed it out at home. It's
Flat 10 on hydrate.
I had a question about like this one. It says how much F702 is required to produce. Okay, so in your version, you left it in grams, and in mine, I have it in kg. Basically the same. Is that okay if I leave it in kg? Same with that.
Yeah.
Yes. And then this one. Grams of hydrogen gas can be prepared from 1 gram of atom of aluminum. So. Do you need to do Avogadro's number and small, because this is the one that you did, and you did not use the Avogadro's numbers. Yeah, go ahead.
It's gram to gram.
Mhm.
So you don't.
It's a gram.
I mean,
So you just don't need those.
right, because I'm not asking for how many molecules. That's Avogadro's number.
I guess so.
In that case.
Yeah. Okay, thank you.
Good.
Answering all of the questions on a separate piece of paper and showing our work, or
Yeah,
we
because
just.
it's on the short setup.
Okay.
And then I gave you the answer, so you'll see the setup. Yeah.
Yeah.
This makes sense today?
Yep.
This is real life. This is what all manufacturing deals with this. Limited reactor.
yeah, okay, I remember doing this a lot in school. Yeah.
Well, the friend of mine, was the general manager of Union Carbide line.
Mhm.
He worked with boxcars, with stuff, boxcars even with product,
Mhm.
and he had to deal with this all the time.
Yeah, no, it's cool learning stuff that it's actually like applicable in real life, it's all the time.
You know, the bicycle thing is real too.
Mhm.
That's, it's extremely simple, and everyone is very comfortable with that.
Mhm.
And then if I started with gram, missing.
Few more moving parts. Oh, I was gonna tell you one thing, the lecture from last Saturday, I don't think you posted it on Canvas, but it's on your YouTube channel. Just thought I'd let you know.
Wait, let me know, let's see, the date is what?
That date, I think, was 3/8. Last Saturday.
Yeah, it's right here, 3/8.
Huh.
Oh, maybe I didn't sync it though. Let me,
Yeah, it's not on my, I just checked on my computer like a minute ago.
okay, yeah.
Okay.
See, the problem is because of two sections, I have to have a third section that glues them together.
Mm,
And when I change the glue, I have to click on sync and then it updates each of the attached classes.
yeah, they make it complicated.
Yeah, so it's syncing now. And
Okay,
thanks
Thank
for
you, Professor.
keeping me up to date.
sounds good.
Yes, sir.
I'm trying to put down for a master's in nursing class.
Start over again.
I'm applying for a master's in nursing program. I hope that soon. And, they said one of the right classes next week is chemistry. And I was wondering, the next chemistry, like up after this class, is that 1A or
Three. 2A and 3A.
what is the next one, like the order that I take the classes?
The program, what kind of program in the beginning? The PA?
It's a nursing program. So like a nurse practitioner.
Okay. You need to check the school. Some of them want you to have 1A and 1B. Others want you to have 2A and 2B. 2A/B is an allied health track. And most of the time, RNs, schools want that. PA and NP, both of those usually want more of a rigorous chemistry. So look at the schools you're applying for, and you'll see what classes they require, chemistry wise.
So but 1A is more rigorous, would
Yeah.
you say?
1A is the most rigorous. 2A is the least. But 2A stresses allied health examples. Like I teach equivalent to 2B at Sac City, and it's called 306. And I have tons of organic and biochemistry examples. If you took the other organic, you get no examples like that. But it depends on the school, and they can be real picky. Also, the other problem is if you're applying to more than one school, sometimes one will say one thing and the other will say another. And then I don't know. The best way to do it would be to talk to your counselor for sure. And they theoretically should know all this stuff. Theoretically.
Okay.
I would take what they say with a grain of salt and then also check on your own individual schools. Just to make sure it's consistent with what counselor told you. They're swamped. And sometimes the schools will change their requirements and they don't update, and the counselors aren't updated, so it's giving them,
Just to remember, 2A is, 1A is more rigorous than 2A.
and 3A and 3B takes 1A and stretches it over 2 semesters. So 3A and 3B is rigorous also, but it takes a whole year to get through it.
All right.
I think it's a better course, but then you have that extra semester to deal with. And they don't have that at Sac City.
Okay.
We have enough problems finding teachers at Sac City. Same with here, they're having trouble finding. That's why they only have 2 sections of Chem A. When I first started here, 3.5, 4 years ago, whatever, they had 8 sections.
Oh.
And they just don't have enough people to teach it. And it's a really needed class too. I mean, seriously needed. What I went over today, starting balancing equations and conversions in simple and complex stoichiometry, they cover it in a week. Like this.
That's intense.
Yeah. That's why this is really, and a lot of people, for example, I taught 1A over a summer a couple of years ago, and I had 6 people from my spring Chem A class. They got A's in my class. The other people were from like UCD, Sac State, University of North Dakota. They all were getting C's and D's because the setups were bad and they didn't use unit cancellation and they flunked it and having to take it over. And my students just, it was still a hard class, but they did well.
Yeah.
So it's needed.
Yes. My counselor said that I need to get all A's in my science classes. So very glad I took your class, this class first. Thank you so much for teaching.
Sure.
Appreciate all your help.
Yeah, I like teaching this class because it helps my students achieve better.
Yeah.
My students that go on. So.
Oh.
No, okay.